Hello, everybody. My name is Nick, and today I'm happy to present my research regarding the numerical analysis of swirl injectors. In short, the goal of my research is to develop a new numerical method of computing swirl injectors because I believe that the main thing that's been holding back this technology is primarily the analytical difficulty of these systems. And what I've been doing is I've been running a lot of empirical testing to gradually improve a MATLAB-based computer model that you can just plop straight into Simulink, right? And facilitate the use and the design of these injectors for engineering systems. So in short, what I've done is I have done two things. I've done a lot of research about the current theories, right? The current state of swirl injector research, and incorporated a lot of the theoretical models that have been implemented. However, I've also implemented a empirical testing and empirical data that I found into a recursive solver that takes a idealized envisaged case of a swirl injector and runs it through a series of checks, right? Recursive checks to output a realistic engineering design perspective, right? Design. So to make this work, right, I've done two types of things, two types of testing. First of all, I did a lot of FEA simulations. So I ran this thing through OpenFOAM using the SimpleFOAM solver, right? And I also made some visualizations using MATLAB and the 3D plotting utility, which is actually surprisingly powerful. But from my simulations, I learned quite a few different things. Primarily, I learned about the criticality condition, which is very important. And as I will later mention, is one of the main design constraints when it comes to this sort of system, as well as as well as just the formation of the air core. So the main difficulty with this is that criticality. So this works on the critical flow that's swirling through a chamber, right? That spreads out, creating that nice liquid sheet that that enhances atomization. But to do that, right, you there needs to be an equilibrium condition inside of the chamber, inside of the swirling chamber, where the flow is critical, right? Otherwise the chamber fills up, right, and you don't get the same kind of flow as you want. So in early low pressure tests, right, I did about 2 years ago, I found that this criticality condition was not suitably met, or at least was suboptimal, right, under low pressure systems. And in reality, right, these pressures are not the kinds of pressures that industry would work with, more about 100 psi or greater, right? So I decided to apply for an RU grant so that I can build a more sophisticated model based off of wider range of data. So I constructed a high pressure test apparatus, I'll show you in a little bit, and tested all the swirl injectors again until I was able to be satisfied with some of the characteristics. Anyway, moving on. This is my MATLAB program that I developed. So as you can see, right, you can plop it straight into Simulink. The Simulink environment is an awesome playground wherever you can, where engineers often create their designs and simulate them before actually building them. And that and by being compatible with the Simulink platform, right, I'm able to make it a lot easier for designers to implement. So right now, this is a prototype, right? We don't have all of this is a simplified version for this that I found the most significant parameters, right? There are some, right, that like nozzle length and such, which I'm still investigating, but from the major sources of kinetic loss and momentum loss, right, are the nozzle radius, inlet radius, and vortex chamber radius, which are the main important things. And I found at smaller scales, the passage length is really important, primarily due to the strong effect of viscosity. See, whenever you have, despite the high pressure, it's not particularly high energy, right, due to the small cross sections, and as a result, you have a low Reynolds number, and you might have to worry about different flow regimes, which is one thing I definitely found with my most recent tests, and just one example of some of the changes I've done to this modeler. Then after that, right, once I have these parameters and I am satisfied with the simulation results, I have this parametric model in SolidWorks, right? That takes my model and turns it into a device that I can print. And using the power of 3D printing, I'm able to create these intricate geometries. Although in the future, I do want to test with even higher pressures, metal based. Since these are also weak, plastic is also weaker, and at the pressures I'm dealing with, it's just a safety concern. So this has been the biggest limiting factor with my research so far. Then after that, right, I take these devices and I run them through this through this high pressure injector. So I just want to show that off. So this is the device I built, right, using a high pressure chamber, a what's it called, pressure transducer, and various pressure control systems. I'm able to finely control and tune the pressure inside of the main chamber, and I feed this with a power washer pump that I basically brought back to life and tuned up and shimmed the regulator and all that sort of stuff for the proper regime. And with these tests, I've been able to gather so much data, so much information, and I've built a model that so far is starting to actually appear relatively accurate. I still need to do more tests, right? I still have a lot of plans I want to implement, primarily with the downstream flow condition. I want to implement a laser anemometer in the future in order to actually characterize using phase Doppler anemometry the droplet distribution in the exit. So that's just a little peek at my research that I've been doing, and I am actually so blessed that I've been able to do this, and I just like to take this. I'd like to thank you all for watching, and also I'd like to really thank the people who've supported me. Dr. Moon who has made this all possible. The RU program for providing the funding to take my little hobby kind of research I was doing in the garage to basically this fantastic lab. And also I'd like to thank the Innovation Day sponsors for making this all possible. So thank you very much for watching, and I hope to see you soon. Bye.